amelinocamelia, and he will talk about quantum gravity phenomenology.
Okay, thank you. Sorry, my computer didn't start. And so what I'm going to say mostly is that some of us were discussing the possibility of Planck-scale phenomenology 10, 12 years ago already, when really data, we were imagining to have data of the quality we have now in some areas. And I will make the point that now that we have the data, we're figuring out that with all this time available, and with the humble objective of having just some rudimentary test theories to confront to data, we are not ready. And we are getting ready now. We should be getting ready now. So the first thing I will show is been my main concern for the last 3 or 4 years, which is that many of us, many who are here in the audience have worked at least part-time on the use of gamma ray bursts to constrain a possible dispersion, in-buffer dispersion of the type you find in certain non-commutative geometries and in certain approaches to loop quantum gravity. Well, the data, the better data, the most useful data from that point of view will be from the from the sources which are farther from us. And for that, you need models, at least test theories, that describe how the momentum dependence of the speed of photons deals with the expansion of space-time. Okay? Because from Z or 4, for example, you clearly cannot do well enough with Minkowski space calculation, which is all that anybody has been doing in this community. Most of it. I will mention an important exception for the last few years. So I think with my students in Rome, which are also looking for jobs and are really very bright, we finally have at least a test theory, a rudimentary test theory to compare to data from this point of view, and with some ideas that are relevant both for doing this when you break Lorentz symmetry or in the perhaps conceptually simpler, not technically more challenging idea of deforming symmetries. I will then comment, I think Liz Moni must have said most of it already, so I will comment briefly on the issue that Sabine raised in the literature recently about non-locality in the case of the deformed symmetry scenario. And you will see that the effort we made of formalizing expansion with the energy-dependent speed of light immediately provided at least a humble framework where you could start explore these issues of non-locality. I will do all this very quickly because I'm of course mostly in love with my latest thing, and what I'm now really excited about is the issue of infrared ultraviolet mixing that came up early this morning, and there is some really striking data situation in precision measurements for cold neutrons that I want to get to. Okay, so the first, the first thing I want to clarify, which is that it's implicit in most speakers working on Planck-scale phenomenology, but I think it has not been fully rationalized, is that we are not even looking for quantum gravity. Okay. This was the traditional idea that we were just going to take the standard model in general relativity and with some brilliant idea fix everything and finish the job of fundamental physics. How sad that would be. But really what we need to imagine, and at least I propose that this is what we need to imagine, is that if we need to really develop a new theory paradigm, if it is true, as many of us suspect, that quantum gravity will need a new paradigm, as different from what we have now, as quantum mechanics was different from classical mechanics, then it's really, if you buy that, and you don't have to, but if you buy that, it's really pointless to imagine that we will get there in one strike of genius. So of course we will have first the old quantum gravity theory. There will be many decades. It was 3 decades for quantum mechanics. It will be many more for quantum gravity, where these new frameworks will start emerging, but we will get just some pieces of the puzzle that don't really make sense, and it will take a long process to have a theory. At first it will be like quantum theory in the first 30 years of the last century. So we have to search for the old quantum gravity theory, which is pretty, it seems easier. It's interesting that we search forward in time for the old quantum gravity theory. But I think to be aware of that is very valuable. And it looks like simpler than looking for quantum gravity, but if we get to it in the discussion, I think it's even harder. Now, as an example, okay, so what I'm imagining is that some of the research lines, many of them will miss. Some of the research lines we are doing for plant-scale phenomenology, many of them will miss, but then maybe not one that we have started now, but at some point, some bright guy, the really bright guy is not the guy that solves quantum gravity, that guy simply doesn't exist, but it's the guy that takes us to the first discovery of first manifestation of this new realm. Okay? Somebody that gets us the photoelectric effect, not the quantum mechanics of Schrödinger and Heisenberg. That guy simply doesn't exist. And probably also the other guy doesn't exist, but that one we can know. And one of the roads we have tried, and the criterion some of us have followed, is not so much what we think is more compelling, but what we can do, of course. That also should not require any defense. As being the study of, since in some quantum spacetimes you do see this opportunity for the speed of photons to depend on momentum, and there has been a huge, well, by our standards, huge literature devoted on this momentum dependence of the speed of photons. The interesting thing is that we were so busy trying to make the case more compelling or less uncompelling that we forgot that sticking to Minkowski space was convenient for the conceptual side because it simplified issues, but it was not really putting us in the position to compare to the data we were asking astrophysicists to provide. The data, as you have heard in some of the talks, especially one yesterday, they come from distances where clearly you cannot even start analyzing the data in a Minkowski framework. So we need to deal with space-time expansion. And actually, the only very few people have tried to make sense of having a momentum-dependent speed of light in an expanding space-time. It's shameful, but I guess most of you, most of those who have not done it like me, have thought about it, but I didn't know what to do with it. Only 2 groups, actually. Nick, who was yesterday with John Ellis and Dimitri and Subir and others, and Sibiran and Jacob, have, for the case of Lorentz symmetry breaking, they have, well, they went into a quarrel between them, as it is normal with these delicate issues, but at some point they came up with a consensus proposal among them. Basically, I'm here summarizing for my own purposes. Of course, you could have a much more general framework, but from the point of view of the relativistic issues I want to address, I will specialize their results to de Sitter space, and so the simplest type of expansion we understand, and to conformal coordinates, which I am actually proposing. If you understand Minkowski space and you want to learn about de Sitter, the best way to start is conformal coordinates. And this is what they have, and this is what has been tested. So experimentalists now have the data, and I guess they figured out that theorists were not even ready with the rudimentary test theory. And so they have compared to data unanimously this setup that through the work of Nick and John, and especially very significant contribution by Sibiran and Louis Jacob, provided basically this formula. Because then when you compare to data, you want to know Delta pi is the difference in momentum of the two photons. Delta t is the delay you would measure, and this is the dependence on redshift. And this integral formula is just standard machinery obtained from the conformal coordinate formulas that look simpler, but they have the same physical content, of course. And here I have a slide which for now doesn't make much sense, because I will comment it on it later. But I just want to, I put it here already, just to show that this prediction for the time delay is rising pretty significantly with redshift. And actually, in principle, if you were in the zeta space, this is, I'm now putting a more realistic cosmological model. But if I was in a zeta space, this time delay would depend quadratically on redshift in the LSB. I'm calling LSB Lorentz symmetry breaking. And there are some other features which are striking of this formula. For example, this is the velocity of photons in conformal coordinates, and you get the same validity feature in, say, moving coordinates. And it's easy to see that if you go far enough back in conformal time, so the very early universe, the speed of photons changes sign. Okay, it's a very straightforward calculation. And so basically, this is a prediction that if you take it at face value, it would mean that from a very far source, times much earlier than us, low energy photons come straight to us. But if you take this formula literally, high energy photons, the highest energy ones, it depends, of course, how high, it depends on h and pi. High energy photons do something strange. They first move away from us, and then I was going to look at the faces. This is just in the formula. They would first move away from us, and then as negative time gets smaller, they would catch up in the right direction. Of course, this happens all very far from us, and it could be a coordinate artifacts, or even, of course, it could be an artifact of the leading order truncation. Okay? Because we are at the, when I'm going to these very early times, there might be a theoretical framework which tells you that when this quantity, not pi, which would be the natural intuition for some of us on the theory side, but maybe there is a theory where this whole thing governs the expansion. Then this thing doesn't happen anymore. Or there could be some theory where this is this funny thing is a coordinate artifact. Surely it's difficult to imagine it would be a physical effect. Although it's a bit difficult to imagine it is a coordinate artifact, in a theory, the idea of this Lorentz symmetry breaking that some of us have been studying for some time is that Lorentz transformations are just classical. You just have a law that breaks. It's like having a medium. Okay, it's like this would be the same effect as having space-time behaving like a medium throughout the universe. So it's very difficult to imagine coordinate artifacts in these cases because you think you know what are the symmetry transformations. But so this is, for example, an open issue that nobody is aware of for the only model that has been compared to data since the data has space-time expansion, of course, imprinted to it. Now let me tell you how finally, well, first of all, let me tell you that there is no, that this particular Casimir, so the crucial, as in the traditional way to do these studies that somehow got established over the last decade, the key imprint of the theorist is to imagine what is the Casimir invariant in the new theory. Okay? And this in conformal coordinates would be what eventually Piran, Ellis, and Nick agreed upon. And I can show you that there is no deformed boost that leaves this thing in mind. Okay. So for example, such a formula is not admissible from the perspective of the deformed symmetries rather than broken symmetries. Keep being going. And let me summarize briefly the idea of these deformed symmetries, as far as we've studied so far. This is the idea that maybe Lorentz symmetry is not fundamental after all, but any departures from Lorentz symmetry would be still compatible with the absence of a preferred frame. So what this program is imagining is a new change in the relativities transformations, just analogous to the one from Galilei to Einstein. So Galilean symmetry is a perfectly good symmetry, but without any relativistic invariant. Then we get to special relativity, where you have no preferred frame. It's not Galilean, but it's no preferred frame. It's just the novelty is an invariant scale, a speed of light scale. And now we are looking for a new theory where you have also the Planck length, essentially, as an invariant scale. We don't really know how to do it. Lee must have spoken about my preferred formalization, which is with Kappa-Minkowski non-commutativity. But to have a preferred formalization without a preferred interpretation is challenging. So Lee is working on one and I'm working on one. But these symbols, the symbols appear to make sense, but without interpretation, operative interpretation is very difficult. The bulk work on this deformed this W special relativity framework has been basically simply at the stage of deformed Lorentz invariance of energy momentum space. And there are plenty of papers from nearly a decade now where the main achievement, and it's admittedly a very small one, was to show that it would make sense to realize deformed Lorentz symmetry in energy momentum space. Formulas like this, where omega is in some sense the energy and pi the momentum, kept is invariant relation without affecting this lambda. This could be so what we meant, this is very little, not only because it doesn't give you a full relativistic theory, but also because for many years it was specialized to Minkowski space, I mean to flat space. There was no room for expansion. Even the Casimir knows about the expansion. There was nothing there. So we now have finally found a way. It seems very easy now that I make you the story in conformal coordinates and everything seems obvious. Maybe it was obvious, but I have tried so many roads that didn't work. This is the one that works, and a posteriori will look like obvious. So we went to conformal coordinates, and there it was easy to guess. Okay, in conformal coordinates, it's easy to guess if you made it work in Minkowski space with this Casimir. Okay, to keep it as a relativistic invariant. In conformal coordinates, it's easy to guess that you would like to try to make this the Casimir invariant. No? Again, as usual, the zeta space is just in conformal coordinates as the Casimir invariant as the Minkowski invariant multiplied by, say, the square of the scale factor.
Finally, why do you need the zeta space? I mean, wouldn't work in any conformal fact
space? Yes, this I'm going to do. This I'm going to do in conformal flat. I'm going to do in FRW. No. In the Zitter I have a special relativity. I mean, the reason why I stay in the Zitter is so that every statement I give you is actually special relativistic or W special relativistic. But this setup is indeed arranged in such a way that you can do it in any conformally flat. And we want to do it in FRW, of course. So if you see the paper, the formulas are for FRW, but I thought it would be easier to show here. And so we have an explicit boost, as usual. I mean, when I write a paper on this, there is some explicit boost written up. And we have an explicit boost that actually leaves these de Sitter-like Casimir invariant. And we get the velocity automatically by construction. We have a construction which is very rudimentary. It's just a Hamiltonian construction, as if you were in classical space-time, which of course doesn't make any sense. But it provides a workable test theory. To the point that we have a prediction for the dependence on redshift. Okay. Of course, our word lines don't do that funny thing that I showed before.
How can you have a prediction if you have no interpretation?
No, this is the opposite. I mean, this has the interpretation, but it does not have the quantum space-time. That's postpoint. This is a very interesting question on which I want to discuss. But the problem we have in non-commutative geometry is that we have the symbols, and we have good motivation of the symbols, but no interpretation so far. This has a trivial interpretation. It's just whatever is on this board, we assume it has the same interpretation as in the classical theory we are deforming, but now the challenge is to understand what quantum space-time would match that. But let's postpone it. This is a bit something. And interestingly, it makes at redshift, at moderate redshifts, it doesn't make a huge difference. Okay? Of course, conceptually, there is a significant difference because we don't have this feature that I showed you in the previous. I'm apparently broken. I'm okay. This feature that I showed you here is just a result of having the conformal. I mean, it was not rationalized like that before, and I came to realize it after 6 months of thinking. But this feature, a posteriori, if you're writing conformal coordinates, is just a feature due to the fact that you have photons which in conformal coordinates have a time-dependent speed, okay, which is actually what conformal coordinates should not do normally, but they are doing in the symmetric breaking framework that have been developed before. Of course, by doing the fully relativistic analysis here, we get this result which is more standard, more closer to the usual relativistic expectation, and we get this formula which, however, with all this work, up to z of order, say 2 or 3, does not make a huge difference, but I've shown here, this is the accuracy of data from the burst we saw yesterday, 090510. And I've just dreamed that we will have that precision going upward to maybe 0.4 or 5. And this is to argue that this difference between the two formulas could be significant at some point. Okay? But it requires optimism because 090510 was a miracle. This I will discuss with the priest after the seminar. One other interesting thing in relation to the talk is that now with this dependence on redshift that we have here, I have here plotted now all the better data we have on in-vacuum dispersion. These are all upper limits, of course. Don't be misguided by the symbols. These are all upper limits, but I'm discriminating between statistical and systematic the best I can. So I have blue statistical and brown systematic. And it's quite striking that the upper limits, I know it means nothing, and so I make no apology for it, but the upper limits are on a straight line. And when I wrote this paper, actually, this is from the paper which is on the archives, with Marciano, Matassa, and Rosati. I didn't know about the Swift issue that was raised yesterday, so I was just not, and in fact I will not change the paper because it's true that they have this precursor, but what it implies is very subtle that we also can discuss. But just for the fun of it, I was just having fun with my periodic breaking. If I say that the Swift precursor cancels 090510, which it doesn't, then I would have that the upper bounds are on a straight line, which doesn't mean anything anyway. Now, what does it tell us about locality? That was the issue that Sabine very forcefully brought to the attention of everybody. Well, this formalism is too rudimentary. My main criticism, Sabine knows, my main criticism is that we know so little about the quantum space-time. That is really too early to make claims of any sort. I mean, even the claim that even my claim that this is a test theory. It's a formula that now makes a definite prediction. You compare to data, but until we have a more refined picture, until you have better, you lose this to compare to data. And if the data start being on that line, this is the way I like physics. My dream is that I still don't understand how it works, but the data start piling up on this line. That's the best of things, If it works and you don't understand why, that would be the best of all. but we really don't understand why, even if it works, but it doesn't work. So my main criticism of Sabina's paper is that we don't really know what we should do. But, well, she proposed that anyway we should look at word lines, somehow with what we know about deforming Lorentz symmetry. And actually this formalization that I had developed for the zeta space could be adapted to that purpose, although with the quotes, because it's still not a full quantum space-time picture. What should be stressed is that Sabina's argument, this is the core of Sabina's argument, Lee must have covered that. It's basically a hard photon going through the origin. If one combines different aspects of what the deformation of symmetry could mean, one could convince himself or herself that a hard photon going through the detector, through the origin of the observer, actually misses the detector for a boosted observer, who is, however, on top of the first observer, is a boosted observer. This would be quite striking. I'm not sure if in a quantum space-time if that could happen, but surely it would strike me. And actually, I think it cannot happen, because you see, if I had a quantum space-time that did that, now this is the previous picture, but I now put another source farther off, and this produces a photon on the same, equally arced photon on the same word line, and it gets split into two, so not even predictively non-local. I don't think there is any quantum space-time that does that. And I guess this should be postponed when we do have more compelling quantum space-time pictures. But what we did with my students is to apply the machinery we had developed for the zeta space, and then, again, Danielle's comments are quite appropriate here. It might make no sense to draw word lines on these plots, neither in Sabina's paper nor in my paper, because we don't have the necessary combination of a theory side and an interpretation of a mathematical physics side and interpretation side to make sense of all this. But here I report the exercise. The interpretation is up to anybody. So I take the Casimir, the H going to 0 unit of the Casimir I showed earlier. So the Casimir that worked for the zeta space, I take the H going 0 unit. Oh, this is the Casimir. This is actually the boost, the deformed boost. And I do a Hamiltonian treatment as I did before, and with Danielle will discuss. In a quantum space-time, it's likely to be very different. And the paper by Lee actually raises some of the issues that should be dealt with. These are the word lines you get, and these are, from the form of the boosts, the transformation of coordinates. And so you get some non-locality of the type that Sabine had imagined. But what you get by construction here is a very critical non-locality. So Alice, assume Alice sees a photon emitted from a certain source. Then Bob sees the photon emitted from the source, but not exactly where the source is. This of course requires cosmological distances for it to be a meaningful distance. So this is what we find. This is more general word lines, but it doesn't add much to the thing. And I will say that in our paper you will not find such a detailed account, but I invite Liz Molin wrote in detail what are the implications of this analysis, what are the residual open issues. I do stress to the experimentalists in the audience that the data must be taken on this, as Lee correctly claims. But also the issues have been raised. It's certainly going to keep us busy for a while, because to understand is a bit like I think it's different. This makes much more sense, and sometimes we can think, but it's again like for the word lines of Piran and Jakob. These strange features at very large distances from the observer. Okay, they could be nothing. I mean, they could be like, of course, in general relativity, we know that the speed of light in a fast expanding space-time, if it's receding for us, is you know, is a coordinate artifact, it can be as large as you want, and it's not that large for local observers. So it could be just a coordinate artifact here, and even in the Lorentz symmetry breaking case. But surely until, as Lee says, is until we have global coordinates in some sense for a quantum space-time, which might take a long time, this will be a lively subject. Now the last 5 minutes just to go to my new law, which must be the greatest one always. And this is now something finally in the infrared. And I also have news, I have 4 standard deviation, which I'm going to talk about it. So very quickly, because there is really here, if that was without theory, this is really without theory. So those who have thought about the quantum gravity problem, they understand what I mean when I say that the deformations of the de Broglie relation are pretty natural. Okay? Many authors have used them, for example, to introduce the Planck length as a minimum wavelength. Okay? If you mismatch momentum and wavelength in the de Broglie relation, it's then very easy to arrange things in such a way that the Planck length is the minimum wavelength, as many, at least semi-heuristic arguments will suggest. Now what we have done with Flavio Mercati is to think, well, but do we have data on this de Broglie relation? I mean, it's shameful. On the de Broglie relation there is not even, you know, on every other part of physics, every 10 years somebody writes a review. Status of tests of special relativity. Status of tests of that. I mean, the de Broglie relation is a fact. Right? In fact, I inform you, the de Broglie relation is a fact of science, untested and unquestioned. And there is nobody writing about it. And there is never somebody writing a review saying, how well have we tested the de Broglie relation? The accuracy of tests of the de Broglie relation on the other end is 0. Because nobody has ever even worried about it. Okay? We were worrying about it. And of course we were looking for small effects. Oh, right. And we went looking for data that would be very precise and possibly in the infrared regime. And we landed on a paper, this was a couple of years ago, we landed on a class of measurements, a highly cited and revered class of measurements by Kruger and others, which actually measured, I mean, they don't describe it like this because if you read their paper, the de Broglie relation is a fact. So they don't even mention the role that the de Broglie relation has in the analysis. But if you look at the description of the experiments, they measure for a beam of neutrons, of very cold neutrons, they measure their wavelength in units of a certain characteristic of the lattice spacing of very fine silicon crystal, and this will be the key point here, and the velocity of the beam of neutrons. So basically, in units of this lattice spacing characteristic of a very specific silicon crystal, and I have to learn on that, they have a measurement of lambda v. So the de Broglie relation for cold neutrons is just wavelength time velocity equal h over m. This is because they're cold. And so we went looking for data with Flavio on independent measurements of h over m for neutrons. Okay? If you want to test, nobody has ever, I think nobody has ever set up, well, the de Broglie relation is tested like, oh, let's see that it's a wave. The particles are waves. These are done. Let's see that particles are waves. But I couldn't find a quote on the de Broglie relation has been tested for 1 part in 100, 1 part in 10 to the 3.
So, what exactly do you consider the Broglie relation? So, I mean, this is a relation, well, in the old quantum theory, it's a relation between the momentum of a particle and its velocity, right?
No.
No.
The de Broglie relation is a relation between momentum and wavelength.
Momentum and wavelength. Yeah.
Now, if the particle is very small, if it's non-relativistic, like a cold neutron,
Yes.
then it becomes, this is still the de Broglie relation. I just specialized it to the case of a very non-relativistic particle. These ultra-cold neutrons are deep in the non-relativistic regime, so I've written P equal mv.
But wouldn't anything that tested the waveform or wave functions of plane waves of some fixed momentum tested the Breuer relation also?
With what accuracy?
So, but this,
Well, I don't know,
but
but
this
I mean, it seems
experiment,
like
for instance,
something
that you were mentioning, this diffraction. So you have a lattice, so you actually measure lambda somehow,
Right.
and then you can measure V or P by this electric field. You change the electric field that accelerates, or if you
Well,
actually use,
it's
or
a
you
prime of flight.
this
It's
is
really a prime of
so
flight.
in this case it's neutrons, but in the original experiments where you can use electrons, for instance, so you have a way of measuring V.
Yeah.
Then with some accuracy you determine H, and
Right.
you can do some analysis, and so you can actually sort of check that
Yes.
you have this universal H with some accuracy. So why are you not satisfied with that?
No, I'm satisfied with that. Nobody's doing it. Very few people are doing it. That's what I'm proposing to do more
So that
carefully.
is done with some accuracy, but you're saying that it could be done to much better accuracy.
I mean,
and
that,
it's
that,
not
that
being
we
done.
should invest some, the
Okay.
Breuer relation is no less important than Lorentz
Okay,
transformation.
okay. So you're
I
saying
mean,
that
the
it's not being
Breuer
done
relation,
with-
the Breuer relation is fundamental. If it's screwed up, we have to close shop as we have done it now and open a new shop, just as much as Lorentz
So you're
symmetry.
saying that it's
But
not
Lorentz
being-
symmetry, there is an update on the limits every few weeks, okay? And on the Breuer relation, I haven't found
So you mean-
somebody who would do
you
that.
mean
So
that
what
it's
we
not
have found
being
is a measurement that has precision of 1 part in 10 to the 8. This is a test. In my mind, they did not present it like this. Okay, and I will can explain why. But this, we found the test. They didn't know it. They were doing it. But we found something that was testing the Breuer relation with precision of 1 part in 10 to the 8. Okay, that was exciting for us because before that, the best we could have is to cook up something with precision of 1 part in 100. So we found this precision of 1 part in 10 to the 8. And then searching in the literature, of course, then you have to compare this measurement of lambda V to independent measurements of H over Mn, of course. Okay? So that you are really comparing the result with the prediction of the Breuer relation. And we ended up, this is just cut and paste from my paper, so 24 doesn't mean much. But this is a paper that did an analysis of H over M. The mass of the neutron and H over M are instead, there is an update every few months on how well the neutron mass is defined. And also these silicon crystal properties, for technological reasons, they are updated very frequently. And with Flavio, we discovered a couple of years ago that actually, if we put the numbers from these reviews, this was the situation in 99 when the experiment was done. Actually, Kruger and others closed the shop 99. And this was consistent between little more than 1.5 sigma, or something like that. Then with Flavio, we found this updated analysis on H over M and D2 to 0. And we noticed this is like the situation nobody had noticed, but we had data in, well, we realized in 2008, but data in 2006 we showed that there was a 2.5 sigma difference between H over M and this measurement. And then, I don't like 2.5 sigma because it could be 90% wrong. It's typically 90% wrong. And at least I want to be 99% wrong. So we waited. We waited for an opportunity to be 99% wrong, and it came. You know? It came, and it's outside the slide. This is a measurement. This is, actually, there has been no improvement since 2008 in the measurement of H over M. But there has been a very significant improvement in the measurement of this silicon, the property of this silicon crystal. And this is what we have in our paper now for H over N D2 to 0. We have a pretty sharp measurement, which is 4 standard deviations away from the result of Kruger's and others. What to say? We stumbled upon this because we wanted to finally find some test of the Breuer relation which had more than 10% accuracy. And we found one with 1 part in 10 to the 8, which is pretty significant. And we went to low energy because of IR remixing. But we have no theory. And chances are we don't need the theory because following on a previous argument that 3 standard deviation are 90% of the time wrong, I can move on to say that 4 standard deviation are 99% of the time wrong. So we might not need the theory. there are the analysis of the systematics of the Kruger and other measurement is very refined. Has been unchallenged for a decade, but now that there are 4 standard deviation, we will have to see it. 99% is systematic. But what and out of this 99% is not systematic. It is something. It could be something. For God's sake, stroke of luck will not harm. But if it is something, it may well be not quantum gravity. I mean, we are in a regime where quantum mechanics could be funny. We have been a community, my generation, frustrated by the fact that nothing new happens besides cosmology. But if this is true, it could be anything, not quantum gravity. What I find embarrassing is that I have 4 standard deviation. I have a little time window until they redo the measurement and they will show there is nothing. To claim that there is something exciting for quantum gravity, and I don't have a model. And so if somebody young in the audience has ideas for a model, please do. But it does look like something that if you want to explain with quantum gravity, it would be IRUV mixing. So it should be something that clearly affects cold neutrons. So far infrared. I will skip fuzziness and a couple of other things. And I'll say that in this spirit, the idea of having an old quantum gravity theory at some point in the future, I think is promising. And I have the master's mistake, which is, I think Einstein is responsible for the idea of having a theory of everything. And I think it's one of the worst ideas ever had by mankind. Thank you.
So before we take some questions, I want to briefly comment on what you said. So on the DSR and non-locality stuff. So if anybody of you is really interested in it, I will reply to the paper that's on the archive that contains all the details. Basically, the thing is that the difference between his calculation and mine is that in his case, as you also said, the non-locality is elsewhere, it's at the source. This is a possibility that I commented on already in my first paper, and it does not really solve the problem, it just moves it elsewhere. So, questions?
Can I reply to the comment?
Yeah, sure. This can go on forever. Maybe you just show the figure again.
Yes, if I hurry well, I think my English is never good, particularly today. But I think the issue was well phrased by Lee. So.
It was well phrased after I kind of commented on it 10 times or so. My viewpoint is that surely these things must be studied carefully. They cannot be, underestimated. But there are two issues that are important. First of all, if we have to do deformed similes, we have to actually write deformed similes. We have to show deformed boosts. So it will be helpful if you produce a deformed boost generator that does that. That will help. It's easy to see why. The only thing you are doing, just show the figures. The only thing you're doing is rotating lines in a plane.
Okay, but why don't we have a boost generator that does that?
Well, you can write it down, but you don't need it.
Well, somebody writes it down. I mean, I have been able to write down anything that doesn't do this. So it's interesting that the debate be on formulas.
This is the same as my calculation. The only thing you have to do is to consider this point, 0, 0.
No, what is different, let me stress to the audience, the difference in the calculation is here. So here there is a boost generator that has been used consistently throughout. This is the key difference. So I think it's very helpful if we all have a proposal for how, so I have a boost generator compatible with this, compatible with this, and this is the result. It certainly helps if other groups, other perspectives produce an equally structured, completely structured framework. Okay, this is the first comment.
Can we just stick with this for 1 second? It is totally true that I did not write down all this stuff, and probably what I have done would not work in more than 1 + 1 dimensions. But the thing is that the final equation that you get, so this is basically C of E. This is the energy dependency of light, if I remember correctly.
Yes.
This is exactly the same phrase that I have used.
No.
Yes?
No, because this is not, this is in one frame, but to have the physics for all observers, to have a relativistic theory, you need to hold the rest. This is not the whole of
in one
physics.
frame, you have it in another frame. You know how this thing transforms. Because then,
No, you don't know it until you have this.
no, this is the energy dependent speed of light. You don't need the transformation in position space to know how this thing transforms because it doesn't depend
This
on
is a word light. This is not energy dependent speed of light.
My
This is a word.
answer
Anyway,
here.
okay.
Maybe.
So anyway, I
would be
will.
very interested to join the discussion later.
Let's do it afterwards with Cephalon. But one important thing is that people read papers and read formalizations. So I would postpone that to that. When people have read papers and formalizations, we will be able to discuss it in a more informed fashion.
So, questions?
About this, the Rowley relation.
Yes.
Do you think that if one really thinks that there is a correction in this formula owing to a quantum theory of gravity, do you think this comes from a modified dispersion relation that is that there is a Lorentz-Ivane violation? Or else it is a quantum mechanics failure, because these are the two main ingredients of our microscopic theories.
Yes, no, Jose makes a very correct question, and also I didn't write enough here. I mean, one way to get, I do have a way to get this this effect, okay, which actually uses something that Jose Cortes had developed some time ago. So you could take a dispersion relation just of the type we have used in the ultraviolet for many years, some of us, and you make a similar deformation but in the infrared. So instead of going like p cubed or p to the 4th, it goes like p. Okay? If you make that ansatz, then you have a free parameter in front. You can adjust the free parameter to match these exactly. But it remains to be understood, of course, how. So it's the same problem as on the other side to understand. Well, one more problem than usual. So first of all, to understand what quantum space-time or quantum gravity could produce such a linear term. And secondly, now also the coefficient, since it is an infrared effect, cannot be the Planck scale. So now the quantum gravity theory must tell us two things instead of one. This is an important conceptual difference. For the first part of my talk, I was doing test theory, waiting for quantum gravity to tell me what is the functional dependence, but I was assuming my guess that the effect is that the Planck scale was roughly reliable. Now, for this infrared phenomenology, of course you cannot put the Planck scale as the scale. Of course, it blows up in your face, in infrared. So the quantum gravity should give you both the functional dependence and the infrared ultraviolet mixing should tell you why the scale. But that scale could be estimated here and it would be a way to determine the parameter you have in your formula.
Giovanni, not try to suggest, and we try to see if you put as the scale, the infrared scale, cosmological quantum one, what coefficient you would get, what is the order of the coefficient?
If you put the cosmological constant, it doesn't work.
Right.
Of course. No, but there is something I've written in the paper. If you put the product of the cosmological constant and the Planck scale, square root. Okay, this is a game, okay? But it works elsewhere.
Yes.
It works elsewhere. If you put the product of the cosmological constant and the Planck scale square root, you don't go too far off. You're in the neighborhood of
The coefficient would be
parameter.
order 1, you mean?
Of order not 1, but of order 10 or 1/10 actually. So nearly. So this is something I'm working on. Because actually I do have in my drawers I have whatever, and so I'm gonna have me soon some way for the cosmological constant to do this, maybe in a QDCiter setup. That would be ideal.
Well, in my approach to quantum gravity, that combination comes in g times lambda.
In 3 dimensions? Because it's very easy in 2 plus 1, I think.
In 3 plus 1, yes.
3 plus 1.
And it comes in starting with the lambda state. And with generalizations of the state, it also comes in.
I need to get your Phone? You are giving me the phone or?
Sure.
Joking. I'm going to read your email.
Okay.
Let's put it this way. You had a question.
Yes, about the Pauli relation. So the precision of 10 to the minus 8 was for neutrons, right?
Yes.
So you know it at one scale.
Yes.
So at a different scale, you don't know.
You don't know. No, I mean, this thing will blow up immediately because if they redo the measurement, I'm sure enough, as everybody in our generation, the thing will disappear. Okay? But in the time window we have to ask for money for something, let's try to get somebody to do tests of the Broglie relation, just for the fun of it, because in principle we are physicists, so we shouldn't take. I mean, the Broglie relation is a fact. If you open any paper in physics, the Broglie relation is a fact. I mean, it's not like a law that connects wavelength to momentum. Momentum is the inverse of wavelength. But these are two concepts with a different operatively sharply defined content. So a physicist in principle is not allowed to say momentum is the inverse of wavelength. Well, physicists say within the de Broglie framework, momentum is equal to the inverse of wavelength, because the two things are operatively well defined independently. So you can measure momentum and measure wavelength.
Another question. Do you have so my intuition was that, you know, for CMB effects, polarization, the energy scale of the photon barrier fluid would just be so low that you would not expect to see any, you know, quantum gravity effects. But do you have the same intuition, or, you know, is our intuition developed enough to make such a, you know,
well, I
assumption?
tried to comment to the talk we had before, that what we have learned in this decade, that there is no energy scale, or say wavelength scale, small enough for us to say, oh, the wavelength of these photons is so small we cannot test Planck scale effects. Because for any small wavelength, for any large, however large the wavelength, there is a distance of propagation big enough. Okay, now, of course, the universe is finite, so this criterion stops at some point, but I think I can convince in a few minutes on a blackboard that even take CMBR photons, you know, and you travel for such a long distance, it would be absolutely not surprising to have a quantum space-time effect to show up. Just the numbers work out in a reasonable way.
But moreover, imagine that we have a P deformation, purely infrared, with birefringence, with the opposite coefficient for. Then it would be important only if the photon becomes sufficiently low energy.
No, in fact, I mean, I don't know if Stefan will. Thank you, Stefan, because I don't know. That's why you were together. I think this is what Stefan maybe was asking. I mean, if you now, I don't feel, I mean, I'm not ready with the ultraviolet. I feel I'm not ready with the phenomenology of the ultraviolet, imagine with the infrared. But if one wanted to buy this infrared story, then it would be reversed. I mean, you would have that CMB8R, the analysis of the CMB becomes doubly good, if you allow me to use a word I like.
That's the title of the picture.
Doubly good, because it's looking to very low energy photons, and if you have the ultraviolet infrared mixing, that's where you want to go, and then propagating over very long distances.
And it would be energy dependent.
And it would be energy dependent. I mean, it would be. We should write a paper this afternoon.
Doubly good. That's, I like that.
But anyway, this is
doubly good.
This is certainly would be very exciting. But if I was very shy of the formalization I had for the ultraviolet part of the talk, I mean, the infrared part was shameful. I mean, if I did not have the data, in fact, I would not talk about it. I just mentioned it because, well, this data scream for a discussion, in spite of the formalization being so premature.
Well, you got a guy right in front of you there.
If he gets us some data that somehow we could make a story that they match the 4 sigma, we're going to be involved.
Okay, so this is the last question.
So I have a very nice question coming back to this de Broglie relation. I mean, what you said is true, but To my mind, momentum applies to a point particle and the wavelength applies to a plane wave. Now, if I want to test the relation, I should make up a system. I should look at a system in which I can simultaneously measure both and look whether they satisfy this relation or not.
Yes.
So this means particle and wave aspects come in simultaneously. Isn't that somehow precisely what we learned?
I think the Nobel Prize was given for that in 1926.
For what? For testing it?
Yes. I mean, if you have a beam, what do you mean by, certainly, I'm joking, but I mean, certainly is, even, in fact, I think this is one of the reasons why we need to test it instead of assuming it. What do you mean by wavelength? When you have a beam of particles, we always imagine that we prepare a beam of particles, but we can analyze it from the point of view of wavelength, say when you do Bragg diffraction. I mean that we analyze it as a picture of the wavelength of the beam. Yet then you can measure the velocity of the particles in the beam by standard, rather conventional methods. So, I mean, I think your question actually provides further motivation because it is something subtle of quantum mechanics. It is a point where quantum mechanics is likely subtle. Because what do we mean by saying that the wavelength is the inverse of momentum? It's pretty subtle because on one side we have the momentum of the particle part of nature. So I would take data there. If I was me, and if I knew how to take data there, I mean, it looks like a place where we should look. I'm not saying there is anything, but it's embarrassing there is not a review. Nobody has ever written. I mean, if you find one, I'm very happy to discover it. We have, with Flavio, we have looked all over the place for one review from the 50s, from the 60s, from yesterday, that would say, how well have we tested the Broglie relation? Even tests of quantum mechanics, there are reviews on tests of quantum mechanics, that the Broglie relation is still just, oh, we have tested that it behaves like a wave, if we do the double slit. But I need, what is the precision? If I put the deformation parameter, how much it is excluded. I mean, I want to do the usual thing that a particle physicist would do, despite it being slow particle physics.
So electron beam double slit experiments don't count, right?
No, they do count. They do count. But if you look, for example, if you compare the precision, I've tried, I have back of the envelope for the double slit. The point is, this parameter that I have now at a level of 1 part in 10 to the 8, you would never see it with the, with the, so you need a very fine way to look at it.
Okay, so thanks for that. So I have a few